When you're doing image classification, your system receives some input image, which is this cute cat in this example. And the system is aware of some predetermined set of categories or labels. So these might be like a dog or a cat or a truck or a plane. And there's some fixed set of category labels. And the job of the computer is to look at the picture and assign it one of these fixed category labels. This seems like a really easy problem because because so much of your own visual system and your brain is hardwired for doing these sort of visual recognition tasks. But this is actually a really, really hard problem for a machine. So if you dig in and think about actually what does a computer see when it looks at this image, it definitely doesn't get this holistic idea of a cat that you see when you look at it. And the computer really is representing the image as this gigantic grid of numbers. So the image might be something like 800 by 600 pixels, and each pixel is represented by 3 numbers, giving the red, green, and blue values for that pixel. So to the computer, this is just a gigantic grid of numbers, and it's very difficult to distill the catness out of this like giant array of thousands or whatever, of very many different numbers. So we refer to this problem as the semantic gap, that this idea of a cat, or this label of a cat, is a semantic label that we're assigning to this image. And there's this huge gap between the semantic idea of a cat and these pixel values that the computer is actually seeing. And this is a really hard problem because you can change the picture in very small, subtle ways that will cause this pixel grid to change entirely. So for example, if we took this same cat, and if the cat happened to sit still and not even twitch, not move a muscle, which is never going to happen, but we moved the camera to the other side, then every single grid, every single pixel in this giant grid of numbers would be completely different. But somehow, it's still representing the same cat. And our algorithms need to be robust to this. But not only viewpoint is one problem, another is illumination. There can be different lighting conditions going on in the scene. Whether the cat is appearing in this like very dark, moody scene, or like in this very bright, sunlit scene, it's still a cat, and our algorithms need to be robust to that. Objects can also deform. I think cats are maybe among the more deformable of animals that you might see out there. And cats can really assume a lot of different varied poses and positions, and our algorithms should be robust to these different kinds of transforms. There can also be problems of occlusion, where you might only see part of a cat, like just the face, or in this extreme example, just a tail peeking out from under the couch cushion. But in these cases, it's pretty easy for you as a person to realize that this is probably a cat, and you still recognize these images as cats. And this is something that our algorithms also must be robust to, which is quite difficult, I think. There can also be problems of background clutter, where maybe the foreground object, the cat, could actually look quite similar in appearance to the background. And this is another thing that we need to handle. There's also this problem of intra-class variation, that this one notion of catness actually spans a lot of different visual appearances. And cats can come in different shapes and sizes and colors and ages. And our algorithm, again, needs to work and handle all these different variations. So this is actually a really, really challenging problem. And it's sort of easy to forget how easy this is because so much of your brain is specifically tuned for dealing with these things. But now, if we want our computer programs to deal with all of these problems all simultaneously, and not just for cats, by the way, but for just about any object category you could imagine, this is a fantastically challenging problem. And it's actually somewhat miraculous that this works at all, in my opinion. But actually, not only does it work, but these things work very close to human accuracy in some limited situations, and take maybe only hundreds of milliseconds to do so. So this is some pretty amazing, incredible technology, in my opinion. And over the course of the rest of the class, we'll really see what kinds of advancements have made this possible. So now, if you kind of think about what is the API for writing an image classifier, you might sit down and try to write a method in Python like this, where we want to take in an image and then do some crazy magic, and then eventually spit out this class label to say cat or dog or whatnot. And there's really no obvious way to do this, right? Like, if you're taking an algorithms class and your task is to sort numbers or compute a convex hull or even do something like RSA encryption, you sort of can write down an algorithm and enumerate all the steps that need to happen in order for these things to work. But when we're trying to recognize objects or recognize cats or images, there's no really clear, explicit algorithm that makes intuitive sense for how you might go about recognizing these objects. So this is, again, quite challenging if you think about, like, if you knew nothing, if it was your first day programming and you had to sit down and write this function, I think most people would be in trouble. That being said, people have definitely made explicit attempts to try to write sort of hand-coded rules for recognizing different animals. So we touched on this a little bit in the last lecture. But maybe one idea for cats is that, we know that cats have ears and eyes and mouths and noses, and we know that edges are, from Hubel and Weasel, we know that edges are pretty important when it comes to visual recognition. So one thing we might try to do is compute the edges of this image, and then go in and try to categorize all the different corners and boundaries and say that, if we have maybe 3 lines meeting this way, then it might be a corner, and an ear has 1 corner here and 1 corner there and 1 corner there, and then kind of write down this explicit set of rules for recognizing cats. But this turns out not to work very well. One, it's super brittle, and two, say if you want to start over for another object category, and maybe not worry about cats, but talk about trucks or dogs or fishes or something else, then you need to start all over again. So this is really not a very scalable approach. We want to come up with some algorithm or some method for these recognition tasks, which scales much more naturally to all the variety of objects in the world. So the insight that sort of makes this all work is this idea of the data-driven approach, is that rather than sitting down and writing these hand-specified rules to try to craft exactly what is a cat or a fish or what have you, instead, we'll go out onto the internet and collect a large data set of many, many cats and many, many airplanes and many, many deer and different things like this. And we can actually use tools like Google Image Search or something like that to go out and collect a very large number of examples of these different categories. By the way, this actually takes quite a lot of effort to go out and actually collect these data sets. But luckily, there's a lot of really good high-quality data sets out there already for you to use. Then once we get this data set, we train this machine learning classifier that is going to ingest all of the data, summarize it in some way, and then spit out a model that summarizes the knowledge of how to recognize these different object categories. Then finally, we'll use this trained model and apply it on new images that will then be able to recognize cats and dogs and whatnot. So here, our API has changed a little bit. Rather than a single function that just inputs an image and recognizes a cat, we have these 2 functions. One that's called train, that's going to input images and labels and then output a model. And then separately, another function called predict, which will input the model and then make predictions for images. And this is kind of the key insight that allowed all these things to start working really well over the last 10, 20 years or so. So this class is primarily about neural networks and convolutional neural networks and deep learning and all that. But there's this idea of a data-driven approach is much more general than just deep learning. And I think it's useful to sort of step through this process for a very simple classifier first, before we get to these big complex ones. So probably the simplest classifier you can imagine is something we call nearest neighbor. The algorithm is pretty dumb, honestly. So during the training step, we won't do anything. We'll just memorize all of the training data. So this is very simple. And now during the prediction step, we're going to take some new image and go and try to find the most similar image in the training data to that new image, and now predict the label of that most similar image. A very simple algorithm, but it sort of has a lot of these nice properties with respect to data-drivenness and whatnot. So to be a little bit more concrete, you might imagine working on this data set called CFAR10, which is very commonly used in machine learning as kind of a small test case. And you'll be working with this data set on your homework. So the CFAR10 data set gives you 10 different classes, airplanes and automobiles and birds and cats and different things like that. And for each of those 10 categories, it provides 50,000 training images, roughly evenly distributed across these 10 categories, and then 10,000 additional testing images that you're supposed to test your algorithm on. So now, if you think about, so here's an example of applying this simple nearest neighbor classifier to some of these test images on CFAR10. So on this grid on the right, each for the leftmost column gives a test image in the CFAR10 data set. And now on the right, we see we've sorted the training images and show the most similar training images to each of these test examples. And you can see that they look kind of visually similar to the training images. although they are not always correct. Right? So maybe on this second row, we see that the testing, this is kind of hard to see because these images are 32 by 32 pixels. You need to really dive in there and try to make your best guess. But this image is a dog, and its nearest neighbor is also a dog. But this next one, I think, is actually a deer or a horse or something else. But you can see that it looks quite visually similar because there's kind of a white blob in the middle and whatnot. So if we're applying the nearest neighbor algorithm to this image, we'll find the closest example in the training set. And now the closest example, we know its label because it comes from the training set. And now we'll simply say that this testing image is also a dog. You can see kind of from these examples that this is probably not going to work very well. But it's still kind of a nice example to work through. But then one detail that we need to know is, given a pair of images, how can we actually compare them? Because if we're going to take our test image and compare it to all the training images, we actually have many different choices for exactly what that comparison function should look like. So in the example in the previous slide, we've used what's called the L1 distance, also sometimes called the Manhattan distance. So this is a really sort of simple, easy idea for comparing images. And that's that we're going to just compare individual pixels in these images. So supposing that our test image is maybe just a tiny 4x4 image of pixel values, then we're going to take this upper left-hand pixel of the test image, subtract off the value in the training image, take the absolute value, and get the difference in that pixel between the two images, and then sum all these up across all the pixels in the image. So this is kind of a stupid way to compare images, but it does some reasonable things sometimes. But this gives us a very concrete way to measure the difference between two images. And in this case, we have this difference of 456 between these two images. So here's some full Python code for implementing this nearest neighbor classifier. And you can see it's actually pretty short and pretty concise because we've made use of many of these vectorized operations offered by NumPy. So here we can see that the training this train function that we talked about earlier is, again, very simple in the case of nearest neighbor. You just memorize the training data. There's not really much to do here. And now at test time, we're going to take in our image and then go in and compare, using this L1 distance function, our test image to each of these training examples and find the most similar example in the training set. And you can see that we're actually able to do this in just 1 or 2 lines of Python code by utilizing these vectorized operations in NumPy. So this is something that you'll get practice with on the first assignment. So now a couple of questions about this simple classifier. First, if we have n examples in our training set, then how fast can we expect training and testing to be? Well, training is probably constant because we don't really need to do anything. We just need to memorize the data. And if you're just copying a pointer, that's going to be constant time, no matter how big your data set is. But now at test time, we need to do this comparison step and compare our test image to each of the n training examples in the data set. And this is actually quite slow. So this is actually somewhat backwards, if you think about it, because in practice, we want our classifiers to be slow at training time and then fast at testing time. Because you might imagine that a classifier might go and be trained in a data center somewhere, and you can afford to spend a lot of computation at training time to make the classifier really good. But then when you go and deploy the classifier at test time, you want it to run on your mobile phone or in the browser or some other low-power device, and you really want the testing time performance of your classifier to be quite fast. So from this perspective, this nearest neighbor algorithm is actually a little bit backwards. And we'll see that once we move to convolutional neural networks and other types of parametric models, they'll be the reverse of this, where you'll spend a lot of compute at training time, but then they'll be quite fast at testing time. So then the question is, what exactly does this nearest neighbor algorithm look like when you apply it in practice? So here we've drawn what we call the decision regions of a nearest neighbor classifier. So here our training set consists of these points in the two-dimensional plane, where the color of the point represents the category or the class label of that point. So here we see we have 5 classes and some blue ones up in the corner here, some purple ones in the upper right-hand corner. And now for each pixel in this entire plane, we've gone and computed what is the nearest example in these training data, and then colored the point of the background corresponding to what is the class label. So you can see that this nearest neighbor classifier is just sort of carving up the space and coloring the space according to the nearby points. Um, but this classifier is maybe not so great, and by looking at this picture, we can start to see some of the problems that might come out with a nearest neighbor classifier. For one, this central region actually contains mostly green points, but one little yellow point in the middle. But because we're just looking at the nearest neighbor, this causes a little yellow island to appear in this middle of the green cluster. And that's maybe not so great. Maybe those points actually should have been green. And then similarly, we also see these sort of fingers of the different, like the green region pushing into the blue region, again, due to the presence of one point, which may have been noisy or spurious. So this kind of motivates a slight generalization of this algorithm called k-nearest neighbors. So rather than just looking for the single nearest neighbor, instead we'll do something a little bit fancier and find k of our nearest neighbors according to our distance metric, and then take a vote among each of our neighbors, and then predict the majority vote among our neighbors. You can imagine slightly more complex ways of doing this. Maybe you vote weighted on the distance or something like that. But the simplest thing that tends to work pretty well is just taking a majority vote. So here we've shown the exact same set of points using this k=1 nearest neighbor classifier, as well as k=3 and k=5 in the middle and on the right. And once we move to k=3, you can see that that spurious yellow point in the middle of the green cluster is no longer causing the points near that region to be classified as yellow. Now this entire green portion in the middle is all being classified as green. You can also see that these fingers of the red and blue regions are starting to get smoothed out due to this majority voting. And then once we move to the k=5 case, then these decision boundaries between the blue and red regions have become quite smooth and quite nice. So this is generally something, so generally when you're using nearest neighbor classifiers, you almost always want to use some value of k, which is larger than 1, because this tends to smooth out your decision boundaries and lead to better results. So if we to kind of, oh, yeah, question? Yeah, so the question is, what is the deal with these white regions? And those are the white regions are where there was no majority among the k-nearest neighbors. You could imagine maybe doing something slightly fancier and maybe taking a guess or randomly selecting among the majority winners. But for this simple example, we're just coloring it white to indicate that there was no nearest neighbor in those points. So we already kind of saw, so I like to, whenever we're thinking about computer vision, I think it's really useful to kind of flip back and forth between several different viewpoints. One is this idea of high-dimensional points in the plane, and then the other is actually looking at concrete images, because the pixels of the image actually allow us to think of these images as high-dimensional vectors. And it's sort of useful to ping-pong back and forth between these two different viewpoints. So then when sort of taking this k-nearest neighbor and going back to the images, you can see that it's actually not very good. Here I've colored in red and green which images would actually be classified correctly or incorrectly according to their nearest neighbor. And you can see that it's really not very good. But maybe if we used a larger value of k, then this would involve actually voting among maybe the top 3 or the top 5, or maybe even the whole row. And you could imagine that that would end up being a lot more robust to some of this noise that we see when retrieving neighbors in this way. So another choice we have when we're working with the k-nearest neighbor algorithm is determining exactly how we should be comparing our different points. For the example so far, we've just shown we've talked about this L1 distance, which takes the sum of the absolute values between the pixels. But another common choice is the L2 or Euclidean distance, where you take the sum of the square root of the sum of the squares and take this as your distance. Choosing different distance metrics actually is a pretty interesting topic, because different distance metrics make different assumptions about the underlying geometry or topology that you expect in the space. So this L1 distance, underneath this is actually a circle according to the L1 distance, and it forms this square shape thing around the origin, where each of the points on this on the square is equidistant from the origin according to L1. Whereas with the L2 or Euclidean distance, then this circle is a familiar circle. It looks like what you'd expect. So one interesting thing to point out between these two metrics in particular is that the L1 distance depends on your choice of coordinate system. So if you were to rotate the coordinate frame, that would actually change the L1 distance between the points. Whereas changing the coordinate frame in the L2 distance doesn't matter. It's the same thing no matter what your coordinate frame is. So if your input features, if the individual entries in your vector have some important meaning for your task, then maybe somehow L1 might be a more natural fit. But if it's just a generic vector in some space and you don't know which of the different elements, you don't know what they actually mean, then maybe L2 is slightly more natural. And another point here is that we can actually, by using different distance metrics, we can actually generalize the k-nearest neighbor classifier to many, many different types of data, not just vectors, not just images. So for example, imagine you wanted to classify pieces of text. Then the only thing you need to do to use k-nearest neighbors is to specify some distance function that can measure distances between maybe two paragraphs or two sentences or something like that. So simply by specifying different distance metrics, we can actually apply this algorithm very generally to basically any type of data. So it's actually even though it's a kind of simple algorithm, in general, it's a very good thing to try first when you're looking at a new problem. So then it's also kind of interesting to think about what is actually happening geometrically if we choose different distance metrics. So here we see the same set of points on the left using the L1 or Manhattan distance, and then on the right using the familiar L2 or Euclidean distance. And you can see that the shapes of these decision boundaries actually change quite a bit between the two metrics. So when you're looking at L1, these decision boundaries tend to follow the coordinate axes. And this is, again, because the L1 actually depends on our choice of coordinate system, where the L2 sort of doesn't really care about the coordinate axis. It just puts the boundaries where they sort of should fall naturally.
이번 참조 동영상에서는 이미지 클래시피케이션 파이프라인에 대한 설명을 들으셨습니다. 본 강의에서는 이 내용을 요약하고 정리하도록 하겠습니다. 이미지 클래시피케이션은 컴퓨터 비전의 코어 태스크입니다. 디스크리트 레벨에 집합이 주어져 있다고 가정하겠습니다. 예를 들면 dog, cat, truck, plane 같은 것들입니다. 예를 들어서 왼쪽과 같은 이미지가 주어지면 이를 cat으로 분류하는 것입니다. 이미지 클래시피케이션에서 문제는 세멘틱 갭입니다. 이는 언어 또는 기호와 같은 다른 언어 표현으로 객체에 대한 두 설명 간의 차이를 특성화한 것입니다. 우리는 이미지를 통해서 고양이를 보지만 컴퓨터는 0과 255 사이에 숫자의 그리드를 볼 뿐입니다. 이 사진은 가로 800 곱하기 세로 600개의 픽셀로 이루어져 있고 3채널의 RGB로 구성되어 있습니다. 챌린지 중 하나는 viewpoint variation입니다. 모든 픽셀 값들은 카메라가 움직임에 따라서 변화하게 됩니다. 또 다른 챌린지는 illumination입니다. 다양한 조명에 따라서 같은 고양이도 여러가지 다른 색깔을 가질 수 있습니다. deformation은 변형입니다. 같은 고양이가 여러 형태의 모양을 띌 수 있기 때문에 이를 모두 고양이로 판별하는 것은 쉬운 일이 아닙니다. 오클루전은 폐색이라고 하는데 객체들은 전체가 보이지 않을 수 있습니다. 제시된 사진처럼 고양이 신체의 일부만이 보일 경우 이를 고양이로 분류하는 것은 대단히 어려운 문제입니다. 클러터는 어지럽게 흩어져 있는 것을 뜻합니다. 백그라운드 클러터는 오브젝트가 백그라운드와 섞여서 알아보기 힘들게 되는 것입니다. 인트라-클래스 베리에이션은 내부 클래스 간의 다양성입니다. 분류해야 될 클래스의 범위가 큰 것들이 있습니다. 주어진 예시에서 고양이들이 다양한 털의 색깔과 모양을 가진 것을 볼 수 있습니다. 이미지 클래시파이어의 함수의 형태입니다. 이미지를 인풋으로 받아서 클래스 레이블을 리턴합니다. 우리는 자료 구조에서 숫자를 소팅하는 것과 같은 알고리즘들을 배웠습니다. 그러나 이미지 클래시파이어는 No obvious way to hard code the algorithm. 알고리즘을 코딩하는 분명한 방법이 없습니다. 예전에는 다음과 같은 시도들이 있었습니다. 고양이 사진에서 find edges, 엣지를 판별하고 find corners, 코너들을 판별합니다. 그렇다 하더라도 여기에서 어떻게 고양이를 판별해내는지를 알아낼 수가 없었습니다. 현재는 데이터 드리븐 어프로치, 데이터에 기반한 방법론을 사용합니다. 첫째로 이미지와 레이블의 데이터셋을 모읍니다. 둘째로 머신러닝을 사용해서 클래시파이어를 트레인합니다. 세 번째로 클래시파이어를 사용해서 새로운 이미지를 이밸리에이션합니다. 왼쪽 아래 트레인 함수를 보면 이미지와 레이블을 받아들여서 머신러닝을 한 뒤 모델을 리턴합니다. 프리딕트 함수의 경우에는 모델과 테스트 이미지를 받아들여서 모델을 사용해서 레이블을 프리딕트하고 테스트 레이블을 리턴합니다. 오른쪽에 있는 트레이닝 셋이 트레인 함수의 인풋으로 사용됩니다. 첫 번째 클래시파이어로 nearest neighbor를 사용해 보겠습니다. 비록 성능은 떨어져서 실제로 사용되기는 어렵지만 이해하기가 쉽기 때문입니다. 트레이닝 함수에서는 모든 데이터와 레이블을 메모라이즈 합니다. 프리딕트 함수에서는 가장 유사한 트레이닝 이미지의 레이블로 프리딕트 합니다. example 데이터셋으로 cfr10이라는 것이 있습니다. 아래 보시는 것처럼 10개의 클래스들이 있습니다. 5만 장의 트레이닝 이미지가 있고 10,000장의 테스팅 이미지로 구성되어 있습니다. 왼쪽에는 트레이닝 이미지들이 나와 있고 오른쪽에는 테스트 이미지가 주어졌을 때 nearest neighbor의 이미지들이 나와 있습니다. nearest 이미지 중에는 맞는 것도 있고 틀린 것들도 있습니다. K nearest neighbor를 계산하기 위해서는 distance metric을 사용해서 이미지들을 비교해야 됩니다. L1 distance 공식을 사용하는 경우 테스트 이미지에서 트레이닝 이미지의 픽셀 값을 각각 뺀 뒤에 그 픽셀의 총합을 구하도록 합니다. 이 예제에서는 4 곱하기 4의 픽셀을 사용하고 있으며 각 픽셀은 0부터 255까지 값을 가집니다. 총합은 456이 나왔는데 최소값 0에 가까울수록 nearest neighbor가 되는 것입니다. nearest neighbor classifier의 클래스를 정의한 것입니다. init 함수가 있고 train 함수가 있고 predict 함수가 있는 것을 볼 수 있습니다. train 함수에서는 트레이닝 데이터를 메모라이즈 합니다. predict 함수에서는 각각의 테스트 이미지에 대해서 가장 가까운 트레인 이미지를 찾고 nearest 이미지의 레이블로 predict를 합니다. 우리는 n개의 example이 있으면 트레이닝과 prediction이 얼마나 빠른지에 대해서 질문을 던질 수 있습니다. 유감스럽게도 train은 O1이고 predict는 ON입니다. 즉, train은 빠르지만 predict는 느리다고 할 수 있습니다. 우리가 원하는 분류기는 그 반대입니다. 비록 트레이닝이 느리다 하더라도 prediction은 빠르기를 원합니다. K nearest neighbor의 시뮬레이션입니다. 이번에는 nearest neighbor의 레이블을 카피하는 대신에 K개의 가장 가까운 점들의 majority vote를 취하도록 했습니다. 아래 그림에는 K가 1일 때, 3일 때, 5일 때가 표시되어 있습니다. 트레이닝을 한 뒤 테스트 이미지를 가지고 실험을 한 결과 맞는 경우도 있고 틀린 경우도 있는 것을 볼 수 있습니다. K nearest neighbor에서 많이 쓰이는 distance metric은 왼쪽에 L1 맨하탄 distance와 오른쪽에 L2 Euclidean distance가 있습니다. 맨하탄 distance의 경우에는 같은 거리를 가지는 점들이 사각형 모양을 가지는 반면에 유클리디언 디스턴스는 원의 모양을 가지게 됩니다. L1 디스턴스는 L2 디스턴스보다 계산이 간단한 장점이 있습니다. 반면에 실제 거리를 잘 반영하지 못하는 사례가 도메인에 따라서 발생할 수 있습니다. 다음은 L1 디스턴스와 L2 디스턴스를 사용해서 각각 시뮬레이션한 결과입니다. 전체적 모양은 유사하지만 자세히 보면 L1 디스턴스 경우 경계선에서 수직과 수평선의 경향을 띠는 반면 L2 디스턴스는 사선의 모양을 띠는 경향이 있음을 볼 수 있습니다.